All right, guys, welcome back to Loving the Physics with Mr. Goldthorpe. Last lesson was kind of crazy. A lot of interruptions and crazy outside noise and videos that didn't work. So hopefully today will be a little bit more smooth. And I thought I would actually start out with a kind of a video that I wanted you guys to see in the first lesson. So let's do that first. Okay. And notice, by the way, that the timer happens to still be there. I thought it would have disappeared during the video. Anyways, the top one is our closed air column at the first harmonic with a node on the left and the antinode on the right. Now just take a look at the video below. And you can see that first of all, the transverse wave is a solid blue going up and down at the antinode. That's the transverse. But notice that they show kind of a sequence of lines horizontally that actually show the true motion of the particles going back and forth horizontally. And we can say the same thing here for n is equal to 3. And if you notice, look at the antinode on the far right-hand side, and you can see that this is where the particles are going back and forth horizontally at the greatest amplitudes. Whereas at the nodes, the particles don't move at all. And here's our fifth harmonic. Remember, only odd harmonics. At the nodes, the particles stay where they are, and at the antinodes, they move back and forth with high amplitude. Again, if you ever want to look at that video again, just scroll back and then try it again. All right, so that one actually shows us the true motion of the particles and then the equivalent transverse wave motion. Okay. Now, this next one I want to show you is just to get us ready for the last example for closed air columns that I want to do as a review. And it'll be another video. More videos!
Waves experiment using sound. More specifically, it's sound in a closed pipe. So what I have is a pipe which is actually open at both ends. At one end I have fixed a speaker, and that's going to form the open end of the pipe. And in the measuring cylinder there's water, so the water will form the closed end of the pipe. The speaker is connected to a signal generator, and at the moment that's set to about 213 hertz. I'm going to show you how you determine when you have a standing wave in the pipe, because you can't see it. So we have to go by what we can hear, and it's where we get a maximum signal emanating from the pipe. So if I turn it on now, and I can adjust the length of the pipe by just drawing it out of the water, and we should hear that loud bit there, indicating that we had just formed a standing wave because the length of the pipe was just right for this frequency. Okay, so that's how.
All right, that's about all I need to show you guys. I apologize for the low volume there, but hopefully you guys were able to hear what he was trying to get across. And I'm going to demonstrate this as well in our next example. So let's go over to it. All right, so here's our example, and I encourage you guys to kind of write this example down first, then we can go through this together. Okay, so what you have to realize is that instead of actually using a speaker on the top, we're going to use an actual tuning fork that's at 768 hertz for this particular example. And we're going to talk about this thing when it actually creates a standing wave. Now, in order to help, let's draw the diagram first. And I'll tell you what I'm going to get you to do to start off with, you'll see why later on. Can I get you just to divide this up into equal regions? Good enough. This will be helpful for our diagram. Okay, now we're going to be analyzing it when it actually is very loud. Okay, so we're looking at the situation where we actually hear it being loud. And if it's loud, that means it must be resonating, it's forming a standing wave. And so what would the wave actually look like? Now, if you look at the top, you'll notice how the top is a nice open end. Do you guys remember if that's going to be a node or an antinode? And for the open end, that's going to be the antinode, where you have maximum amplitudes. And then what I'm going to get you to do for each of the divisions, just write down ANA all the way along for the standing wave that gets produced. Okay, now let's actually draw the wave. Now I'll tell you what, I'll choose, let's say dark green for this. So the antinode, remember we go on side to side, and the node is in the middle. If that helps you draw this thing, middle, side to side, middle, side to side. Now we start on one side and draw the classic kind of sinusoidal wave or sine-shaped wave. Steady. Okay, and then we'll do the same thing on the other side. All right, so this would represent what the standing wave would look like if it is loud. This only happens when you hear a very loud sound. Good. Now, if you remember when he was doing this demonstration, he was lifting that tube up. And when he lifted the tube up, the water level went down. And the water level represented the closed end, because we have to have a closed air column. Now I'm going to use blue for this. It'd be very appropriate for water level. Now if we start at the very top, and when we lift this tube up, the water level goes down. So I want you to imagine the water level going down like this. The question is, where does it have to get to create the first loud sound, the first standing wave? And the answer, by the way, is if it's at a closed end, closed ends have to be nodes. So here, if I draw that, and I'll draw it like water, when the water line gets down to that level, that would be the first time you would hear a loud sound. And so we will call this the first resonant length, or L1. Okay, so this is a resonant length 1. That's where you'd hear a loud sound. So far, so good. But after that, we're going to continue to go down. What if we actually continue to go down? Well, the sound would go back down to very quiet. And the question is, where do you have to get to make it loud again? Now, you may be tempted to put the next water line at the antinode, but remember, it has to be a node at the water line at the closed end. So the level would have to be down here. And if I extend out this length, then this would be called L3. Okay, this is your third harmonic. Remember, only odd harmonics actually exist here. And similar to the idea, here's L5, etc., going down. So as you lengthen that tube, you'll hear multiple loud sounds, depending on which resonant length you happen to be at. Okay, now let's take the question on. Now what we're looking for is we're looking for the length of the air column for the third harmonic. We're basically looking for L3. And you'll notice we know what the frequency is. So we've got F and we know V. And let's start out with the universal wave equation. So we actually have V is equal to F lambda. So that means we can find the wavelength. V over F, or simply 340 divided by 768. Let's get our trusty calculator here. So about 0.4427 meters. Okay, so that's a fixed wavelength of the standing wave. Now we're looking for the length for the third harmonic. And I guess just a reminder, you guys, what's the distance from antinode to node? If you remember, that's 0.25 lambda, okay, between node and antinode. That's why we have to use the 0.25 formula. So I'll do that one next. So put a line underneath this. Now we do L is equal to N 0.25 lambda, which comes out to be, it's the third harmonic here, times 0.25 times 0.4427. Essentially just multiplying it by 0.75. And I get about 0.36, so 0.332 meters or 33.2 centimeters. Good. So there's another classic closed air column question. Okay, let's move on to our other type of air column. So now we can talk about open air columns. And in an open air column, now it'll be open on both ends. So as you can see in my diagram below, we have some kind of a source vibration, and I'm just going to walk you through it really quickly, kind of what we talked about before. With that source vibration, we send waves in, if you wish, towards the left. When it gets to the open end, remember that's going to be free end reflection. So it bounces back. And we have another open end on the other side, so we get again free end reflection, and that causes it to bounce back. And if we kind of highlight those two, these two therefore come towards each other and start to interfere with each other. And if the frequency of this matches the natural frequency of the air, they form a standing wave. That will make it resonate, become very, very loud, as a lot of those musical instruments are very loud. So that's the basic idea behind an open air column. And to see examples of it, well, pretty much every wind instrument we have are open air columns, open on both sides. So you pick your instrument. Okay, so all of those work. So if you're a musician, here you go. This is for you. Now, as we did before, let's take a look at the math for open air columns of some length L. So again, we start with the first harmonic, and I'll just go blue here. So remember, on an open end, is it a node or an antinode? So this one has to be an antinode here, and it has to be an antinode on the other side. And when you're at the first harmonic, or the fundamental frequency, this is where F1 is equal to F0, the lowest possible frequency, gives us the simplest standing wave, which means there'll just be one node in between. All right, let's talk about what the wave actually looks like. So I'll just do, let's say I'll go green. So for the antinode, remember, dot on the top and the bottom, node in the middle, antinode top and bottom. And that looks like this. It comes down to here and goes up to there. So this is what we call the equivalent transverse wave kind of representation of it. Let's briefly again talk about the real motion of the particles, kind of like the video I showed you at the beginning. Remember, at the node, let's do this in red, at the node, this is where things are at rest, so the particles just stay at rest at this given location. But at the antinode, this is where you have maximum amplitude or maximum displacement, and they'll be moving parallel to the wave motion, going back and forth, back and forth. Okay, so that's the real motion of the particles in red, but we show it in green as an equivalent transverse wave. Okay, now, do you guys remember, again, what's the distance between antinode and node? And that was 0.25 lambda. But you'll notice there's one on that side, but there's one on the other side as well. We have 2.25 lambdas. Add those two together, you get 0.5 lambda. So we discovered that here the length will simply be 0.5 lambda. And you might recognize that's the same formula as a stretched string. Now, the next question is, when we go to the second harmonic, if we happen to believe, let's just say that the first harmonic, and again, I'll just choose a different color here. Let's say the first harmonic is 100 hertz. Keep the numbers easy. Second harmonic, if you remember, would be 200 hertz. Multiples of the fundamental. So, therefore, we can say that F2 is equal to 2F0. Now, the question is, what happens to the wavelength? So remember, if you double the frequency, you half the wavelength. So what we're going to do is we're going to divide this up into a half. And remember, in the first part, you draw that entire fundamental. So this would be antinode and this would be an antinode and a node in between. So I guess I'll do this in green so I'm consistent. So dot here, node in the middle, dot here, dot here. Goes like that, goes like that. Okay. So we collapse it down. That means in this case here, remember, if f gets multiplied by 2, lambda gets multiplied by a half. Inverse relationship, assuming the speed stays constant, which means the medium stays constant. Now let's just extend it right to the end of the diagram. Then we have NA. Notice that we have an antinode at the open end, which means this will exist. This will exist. So then we can continue our diagram. You'll do a better job than mine. I should have put a dot in the middle where the node was. Anyways, you can see now why we want to put a dot where the node is. But here now is our diagram. And remember that, again, if you want to kind of count these things up, that's 0.25 lambda, and so is this. So together, that whole thing is 0.5 lambda, and we have 2 of those. So if we want to make a general formula, in this case, L will be equal to 2.5 lambdas, again, just like a stretch string. Okay, so it turns out every harmonic exists, and they use the 0.5 lambda formula. So now we can summarize this. Here's a summary with maybe prettier pictures than what I had there. And again, remember, every harmonic actually exists. And when it becomes an open air columns, we still use Fn is equal to Nf naught. So again, if n happened to be equal to 4, as we have right here, that's 4 times the fundamental frequency. And if you'll notice, there's 1, 2, 3, 4 of those. So there'd be 4.5 lambdas. So that's still accurate. And again, if you use lambda, this still represents the speed of sound in air. Good. Well, what do we do next? Well, believe it or not, we're pretty much finished. I just have to show you a quick example. So I'm going to go under, oh, wait. I know what I was supposed to do. Nope. I almost had the right idea. There it is. Okay, here's your activity. So we're just going to do a conceptual example for this one. So here we have a huge trombone. And what we're going to do is we're going to shorten the trombone. We're going to take it from a long trombone to a short trombone. The question is, if we assume that it stays at the same harmonic, the question is, what will actually happen to the sound? What happens to the pitch of the sound that it produces? Okay, I want you guys to give this one a try yourself. Very important question. Make sure you justify this using the principles of wave theory. Okay, let's see how you guys did. Well, if we assume it's on the same harmonic, in this case, the fundamental, then we started out with a long fundamental, but then, of course, this shrinks down to a shorter fundamental. It's the same harmonic, but the wavelength has definitely gotten shorter. So you can see this is because L and lambda have a beautiful direct relationship. So shorten the length, shorten the wavelength. So that's the first thing we need to prove. But what's the relationship between frequency and wavelength? And based on lambda, F and lambda have an inverse relationship. But remember, this is only going to be true if the speed here stays constant. Do you guys remember what determines the speed of a wave? Answer? The medium. So if we stay in the same medium, same temperature, etc. of the air, then the speed will stay constant. They have an inverse relationship. So therefore, if the wavelength decreases, then the frequency increases, and therefore it's going to go, okay, it's going to go up in frequency. Good. Well, that's about it. It's a pretty short lesson today. I hope you guys were able to love the physics at least a little bit, and I'm looking forward to teaching you guys again. Take care.